Hello and welcome to helpyourmath.com. In this video, we're going to look at the graphs of the other trigonometric functions, including tangent, cotangent, cosecant, and secant, although not necessarily in that order. We're going to start with the tangent graph. So we have y equals tangent of x. And before we talk about the domain and the range and filling in kind of all of this information about our tangent graph, let's fill in the table at the bottom because hopefully that will help us. So we're going to look at some key points, although we're probably going to look at a few others just to have some reference when we actually go to graph. So remember, tangent we can either consider to be y over x or sine over cosine. So as I go through and fill this out, we just want to remember we're talking about y over x or sine over cosine. So tangent of 0, that would be 0 over 1, which is 0. Tangent of pi over 2, that would be 1 over 0, which is undefined. Pi would be 0 over something, so that would be 0. 3 pi over 2 is going to be undefined again, because that's where x is 0. And 2 pi brings us back to 0, so it will be 0. So this kind of gives us some idea of what we're talking about here, and we can see that we do have some restrictions on our domain. There are some things that we're not allowed to plug in for the domain, so let's talk about that. Anywhere where the domain gives us a value that's undefined, we need to pull out because we're not allowed to actually plug those in. Those are actually going to end up being, well, we'll get to that, but they're going to end up being vertical asymptotes. So when we're talking about the domain, let's see, so we have pi over 2, there's a problem. 3 pi over 2, there's a problem. If you use inductive reasoning, you might say 5 pi over 2 is going to be a problem and 7 pi over 2, and you would be correct. So the domain, we're going to say the domain is going to be x such that, so we're going to use set notation here just because while it's complicated, I think it's still easier than any other type of notation. X does not equal, so how do we force these odd numbers? Well, we're going to say 2k plus 1 times pi divided by 2, where k is an integer. So an integer, this means k is an element of, and then this is a fancy way for integer. That's a z with the diagonal. It's kind of like a double. I have a hard time drawing them. That's better. So the diagonal line is actually a double line. That would be set theory notation for integers. So the domain is x such that x does not equal 2k plus 1 times pi over 2. That's going to force, the 2k plus 1 is going to force the odd numbers. That way, whatever integer you plug in, whether it's 0 or 1 or 2, 2k plus 1 will always be odd. And then we're also saying that k has to be an integer. Okay, so let's look at the range. It looks like the range is just 0. That doesn't seem right. Let's look at some other values just so we can compare and see what we come up with. So let's start with pi over 6, which would be 30 degrees, and tangent of pi over 6 would be root 3 over 3. Pi over 4, tangent's 1, and pi over 3, tangent is the square root of 3. So we do see that there are some other values, and those are just the very common ones. Those are not the only ones. We could also, all 3 of those are in quadrant 1, and it actually turns out that the range is all real numbers. We're going to obtain anything and everything in our tangent range. So we can say negative infinity to infinity. A period for a tangent graph? Well, we're going to define a period as the space in between any two undefined things. So from pi over 2 to 3 pi over 2 gives us a period of pi. Next, we want to look at the x-intercepts. Well, the x-intercepts are anywhere that we see a y for going across the bottom row here. And let's see, it's 0, it's pi, it's 2 pi. Inductive reasoning tells us the next one will be 3 pi, 4 pi, 5 pi, negative 2 pi. So the x-intercepts, we're going to define x comma 0, where x is equal to, and then we can just say k times pi, and k is an integer. So we're going to use this notation quite a bit here. The y-intercepts, now I say intercepts, but of course a graph can only have one y-intercept, and we can see it's right here at 0, 0. Now, with the vertical asymptotes, there are infinitely many vertical asymptotes. There's one at pi over 2. There's one at 3 pi over 2. There's another one at, you guessed it, 5 pi over 2. So we can just say x equals, and we'll just use the same notation from our domain, but this time we're actually going to say it equals because we're talking about the equation of the asymptote itself. over 2, and then we're just going to say k is an element of the integers. Okay, so there's the 5 key points, which isn't super helpful. Also, the 3 examples that I did, pi over 6, pi over 4, and pi over 3, they all have positives, but there are negatives, right? Because tangent can be negative. If we're talking about a tangent in between pi over 2 and pi, for example, or in between 3 pi over 2 and 2 pi. So let's see what this looks like. So we have 0, 0. We're going to do pi over 2 right here, pi, 3 pi over 2, 2 pi. Next would be 5 pi over 2. This would be 3 pi. Going the other way, we'd have negative pi over 2 over here, negative pi, negative 3 pi over 2, negative 2 pi, and so on and so on. So we would have an asymptote here. We would have an asymptote here. There's going to be one here. There's going to be one here. And these should all be nice straight vertical lines. It's just hard to do when I can't touch my wrist to the screen because it'll mess it up. Okay, and so then what these end up looking like, so remember where we have our zeros, we have a 0 here, 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 here. There's going to be one there. There'll be an asymptote here. We're going to get really fancy. And then what these end up looking like is they sort of look like cubic functions. So they're going to come down and then they'll go up like this. And each one's going to do that. Now I say it looks like because remember a cubic function would be able to go on in either direction for x, but we're kind of confined here by the asymptotes. And that's the graph of y equals tangent x. For our next example, we're going to look at the graph of y equals cotangent of x. And again, what we'll do is we'll fill in the table first, and then we'll talk about the rest of the information about this graph. So we might recall that tangent, this was 0, this is undefined, this was 0, this was undefined, and this was 0. Well, cotangent is going to be the exact opposite of that. So this is going to be undefined, and this will be 0, and this will be undefined, 0, and undefined. And just to look at a few more, just so we have a little more to look at, if we look at our pi over 6, pi over 4, and pi over 3, so pi over 6 was root 3 over 3. Here, it's going to be the square root of 3. Pi over 4, tangent is root 2 over 2. Sorry, tangent is 1. Let's try that again. The reciprocal of 1 is 1. And then if we have pi over 3, that would be root 3. And the reciprocal is root 3 over 3. So just so we have some idea of what's happening there. Okay, so now the domain, we see we have issues with our domain. It looks like we have issues at 0, pi, 2 pi. So what we're going to say is we're going to say x is in the domain such that x does not equal k times pi, where k is an integer. And the range, so it's a little bit hard to tell again, but actually the range will be the same as tangent. It's going to be from negative infinity to infinity. The period for this will go from, so one undefined to the next, so 0 to pi, so the period will be pi. X-intercepts, so x-intercepts are where there are zeros in that cotangent column, so at pi over 2, 3 pi over 2, so we could say x comma 0, where x is equal to 2k plus 1 times pi over 2, and k is an integer. The y-intercept, right, there's only one, just like last time. Is there a y-intercept? No, because it's undefined, so we would say none. And then the vertical asymptotes, well, that's going to be like just like the domain, except it's instead of saying not equal to, we're going to say is equal to. So we can say x equals k times pi, where k is an integer. K is an element of the set of integers. Then I looked at the 5 key points, so we're going to start with our vertical asymptotes here. And I'm going to do the best I can. And I'm going to, actually, before I do that, I'm going to label this. This is going to be pi over 2. This will be pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. Over here is negative pi over 2, negative pi, negative 3 pi over 2, gross, negative 2 pi, negative 5 pi over 2. I think I've squished those in enough. Okay, so let's draw our vertical asymptotes first. So we have one at 0. We have one at pi, 2 pi, 3 pi, negative pi, negative 2 pi, negative 3 pi. Okay, the next thing we want to look at are the x-intercepts. So that's going to be exactly in between the asymptotes. So there, 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 and there. And there'll be one there. And then what does the rest of the graph look like? Well, I mean, we could graph the 3 points, but they're not super helpful. So what we're going to do instead is I'm just going to tell you it's going to look just like a cubic function. It's going to be very similar to, but a negative cubic function. So it starts up and then it goes down. Starts up here, cuts down. Starts up here and cuts down. Starts up here and cuts down. Cuts down. Cuts down. This one is just going to end here because I ran out of graph. And that's basically the gist of a cotangent graph. The next graph we're going to look at is the secant graph. So secant, you might recall, is the reciprocal of cosine. So we're going to compare cosine to secant. And again, just like with the other two, we'll start with the table at the bottom. I'm also going to add those additional rows of pi over 6, pi over 4, and pi over 3. So filling in our table, cosine of 0 is 1. Cosine of pi over 2 is 0. This is negative 1, 0, back to 1. Cosine of pi over 6 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. And cosine of pi over 3 is 1 over 2. So secant is going to be the reciprocals of these. The reciprocal of 1 is 1. The reciprocal of 0 is not a thing. It's undefined. The reciprocal of negative 1 is negative 1. The reciprocal of 0 again is undefined. Here it's 1. This would end up being 2 root 3 over 3, because if you took the reciprocal of root 3 over 2, that root 3 would get moved down to the denominator, and then you'd want to rationalize. The reciprocal here would be root 2, and the reciprocal here is 2. So this gives us a very small glimpse, but not super well-rounded, well-balanced, because we're only looking at these values, which happen to fall in between 0 and pi over 2. We want to keep in mind that there are values between pi over 2 and pi as well, and pi and 3 pi over 2, and so on and so on. Okay, so the domain. Is there anything that leads to an issue? Yeah, there's a problem here. There's a problem here. There's going to be a problem at 5 pi over 2. So we have the same problem that we had with the tangents. So we would say the domain is x such that x does not equal 2k plus 1 times pi over 2, where k is an element of the integers. So that's going to provide the odd numerators, the 1 pi, 3 pi, 5 pi, is by defining it like that. And I know it's complicated, but it's the best that we have. Next, we have the range. So it's a little bit hard to tell, and again, just because of the values that I chose, but it turns out that the range will never have a y value in between negative 1 and 1. So the range is going to go from negative infinity to negative 1, including negative 1, because I see here we have negative 1. Then it's going to take a break, and then it will bounce back from 1 to infinity. Now the period here can be a little bit weird. In fact, it's even hard to see, but it's basically like, where do we begin, and then when do we get back to the beginning again? And that would be from 0 all the way to 2 pi, right? Because we have to get that negative 1 as well. So a period here for the secant graph, unlike our tangent and cotangent graphs that had a period of only pi, the period here is 2 pi. The x-intercepts, so we're not going to find any x-intercepts because nothing ever goes in between negative 1 and 1. So we would say none. The y-intercept, is there a y-intercept? Yeah, because we can plug in 0 for theta, and we're going to have a y-intercept at 0, 1. Then lastly, the vertical asymptotes. So we're just going to steal from the domain, and we're going to say they're defined by x equals 2k plus 1 times pi divided by 2, where k is an integer. And that's going to provide that pi over 2, 3 pi over 2, so on and so forth. Okay, on to the graph of our secant graph. So again, I'm just going to label this as pi over 2, pi, 3 pi over 2, 2 pi. Let's go into the negatives as well. Negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. Next, let's do our vertical asymptotes. So the vertical asymptotes are at pi over 2, 3 pi over 2, 5 pi over 2 would be here. There'll be one here at 7 pi over 2 if I continue labeling. There'll be one here, and here, and here. And let's just close it out. Gorgeous. Okay, next one we might want to do is put in those like local minima and maxima. So that would be where the ones and the negative ones are. So here we would have it at 0, we have 1. At pi, we have -1. At 2 pi, we're back at 1. That must mean at 3 pi, we're back at -1. Negative pi, we're down at -1. Back up to 1, back down to -1. And then this graph, so tangent and cotangent sort of resembled cubic functions, sort of, because they were contained by those asymptotes. Well, our secant graph is going to kind of resemble a parabola, or actually a whole bunch of parabolas. So it's going to be like this, and this. Ooh, that was gross. This. No, let's just try again. Okay, good. And then it'll be down here, and it'll be up here, and down here, up here, and down here. And what's really cool, I'm going to change the color on this pen. What's really cool is to see this with the cosine graph. So let me see if I can change the pointer. Pink color. We'll make the cosine graph blue. So the cosine graph would actually look like this. And so you can kind of see the reciprocalness happening there, which I think is pretty cool. Before we look at the cosecant graph, we'll look at the table first, and we'll include our pi over 6, pi over 4, and pi over 3. So starting with sine of 0 is 0, sine of pi over 2 is 1, pi would be 0, 3 pi over 2 is -1, 2 pi is 0, pi over 6 is 1/2, pi over 4 root 2 over 2, and pi over 3 root 3 over 2. We're going to use that to fill in the cosecant. So cosecant, reciprocal of 0 is undefined, reciprocal of 1 is 1, here we have undefined, -1, undefined, and then in between 0 and pi over 2, this would be 2, square root of 2, and 2 root 3 over 3. Okay, so now we're going to use this to identify other key things about our cosecant graph. The domain, do we have restrictions? Yeah, we do. We have an issue at 0, we have an issue at pi, 2 pi. So we're going to say x such that x does not equal k times pi. And we're going to say that k is an integer. So k is an element of the set of integers. The range, so if we look at the range here, much like the secant graph, the range is going to go from -infinity to -1, and then it's going to stop, and then it's going to go back to 1 to infinity. A period here, so again, we're looking for a complete cycle, and the complete cycle, it's a little bit hard to see because it's not super clear, but the cosecant period will be the same as the sine or the secant, and it's going to be 2 pi, because it has to complete, it has to go from undefined to 1 to -1 back to undefined. So it's just in between those asymptotes there. The x-intercepts, do we have x-intercepts? No, we don't. What about a y-intercept? So that would be right here where it's undefined, so we don't have a y-intercept either. Vertical asymptote, so we get to steal from the domain. It's going to be x equals k times pi, where k is an element of the integers. And now we can set up our graph. So this is going to be pi over 2, pi, 3 pi over 2, 2 pi, negative pi over 2 over here, negative pi, negative 3 pi over 2, and negative 2 pi. Setting up our vertical asymptotes, so there's going to be one here at negative 2 pi. If I labeled this would be negative 3 pi. Here we have negative pi. Here we have 0, pi, 2 pi, and 3, oh, gross, and 3 pi. Okay, and then what I suggest doing is just graphing those ones and -1s. So at pi over 2, we're at 1. At 3 pi over 2, we're down to -1. Up to 1, down to -1. Here we're down at -1. Oh, I don't know why I skipped down there. That was weird. Let's try that again. -1, -1. Okay, up to 1, down to -1. This would be up at 1. And again, just like the secant graph, this is going to be like parabolic-y looking. So it's going to like this. I guess technically there's one here. And up here. Oh, I missed. You can pretend like it hit that point here, and here, down here, up here, and down here. And those are the rest of the graphs for trigonometry.